Thank you, Nick. Good morning. Well, we live, as you know, in Turkey at high risk of earthquake, like United States and Japan. After our one major earthquake happened in one southern of Turkey, we have started a project to examine the elevators and see what happens after earthquake inside. Well, there are three major earthquakes happened, as you can see in 2 months' time. And we have observed 25 elevators after these earthquakes. As you can see, they are majorly in traction type, a couple of hydraulics and MRLs. Well, when we look inside the shaft, we have observed that almost all elevators, guide rail fastening systems, mainly brackets, were bent, and some bolts and T-clips were cut because of this seismic force or other issues. So we start to work focused on this issue. Well, mainly we try to model and analyze the guide rail brackets, some bolts, and the T-clips separately. That is why we have some search on these fastening systems. Right? When we checked in installation in Turkey, the installers prefer this type of T-clips, so we focused on this kind of T-clips. I know there are different kinds of clips, but we just search on these types. If we look the acting loads on this system, the first one is the buckling load, as you can see, and the vertical load makes the guide rail buckle. And if we transfer to the brackets and the bolts, we realize that we have some shear effect and the tensile effect on these elements. So we are going to try to calculate and test according these acting loads. When we look at the literature, we found some mathematical equations to express the shear force for bolts and the T-clips separately. And we prefer and select one bolt diameter and T-clips diameter. Then we calculate these forces. And later on, we have tested separately bolts and T-clips and compare the results. We found one British standard is related to test rig for shear and the tensile test. Then we adapt it for our work and use this principal sham for the test apparatus. So we placed either bolt or the T-clip here, and then we press it. That is why we have developed two components. One is the male, another is the female element for testing both M12 and M16 bolts and T-clips. These are changeable heads. We placed in these upper and lower base plates. We fixed in the middle, so it is changeable. So if you have a different size or different diameter of T-clips or bolts, so we may replace for the new one, so we can manage to test. Then we fixed in our test machine, and then we applied the force to sides, and then we observed the result. This is the hydraulic universal test machine, which we found in our department, and we placed this developed apparatus and test several times for bolts and T-clips. And of course, we tried to find out the tensile test, and we placed this special equipment for testing both bolts and T-clips, loading the tensile force. This test procedure was adapted from BS standard, and we follow the same rule, and we repeat 5 times for each component, and we get the speed which indicate in this BS standard. So we follow the regular standard. Unfortunately, we have no any Turkish standard for this test, so we just found the British one. And if we look at the test results, we examine under static load separately, and we load until the fracture points, and we repeat 5 times. And we get this table, and we can get this graph, shows that the bolts and the shear test results, well, these errors coming from the comparing with the mathematical calculation. Some of them is quite similar, but we have some differences when we compare the results. Also, we managed to tensile test. There is no any mathematical rule to show the tensile one, so we just collect the experimental results. We can get the 4 bolts and the T-clips separately. We found errors, and we understand that these errors are coming from the test rig tolerances and machine part precisions, and also another reason is coming from some coefficients in numerical calculations. After the test, these are the photos of the bolts and T-clips, and we observed the damages on the T-clips. We have seen the similar damages on the site search. I mean, after earthquake, we checked some bolts and the T-clips. We have seen the same structure of damaged T-clips. Then we tried to get the knowledge about the real working condition. In our indoor test suite, we have one steel structure to test some experimental work. Then we mimic to empty car case and a fully loaded car case, and we try to collect the data coming from the working condition. So we placed a donut type, we call donut type sensors on the bolts or the T-clips, and we connect via interface, and we have a computer program to collect and transfer to map. Well, in our test suite, we have T90 type guide rail. We have fixed with M12 T-clips, and these are the preloading to be tightened these T-clips. we have chosen 3 different forces. The limitation is coming from the donut sensors because we could not apply over 3,000 newtons for these type of donut sensors. So this is our limitation. And here are the sham to show the sensors positions. So we have 4 of them, and we fixed in this lower and upper brackets. This is Turkish term, left and right. So we placed on both right position. And later on, we move one of them and we place the opposite one. So we have to check left and right guide rails and upper and lower guide rails. And we increase the forces, acting forces, during the safety gear operation. We try to stop the car, test car, on the bracket in the same level, and we try to stop using the safety gear in the middle of 2 brackets. So we're going to see the effects. And how we can do these tests? Well, we have load small pieces of casting weight to get the real empty car case. So we place 10 pieces, then we get the empty car weight. Then we load 46 pieces to mimic the fully loaded case. So we repeat the test for these things. These are the screenshots from the software which we are going to read from sensors. So C1 and C2, let me go back, shows the number of sensors. So we are going to see the graphs like that. And we collect all the points, and during the safety gear operation, so just running condition, then we trigger, then the safety gear has operated, and we collect the force values. So these are the plots. Shows this point is the preload 2,000 Newton. This is 2,500 Newton, and this is 3,000 Newton preloading conditions. And these are the test results reading from the sensors. So we both tested 2 different situations, and this is the empty car, this is the loaded car position. So we managed to read via sensor and to collect the forces acting on the brackets and the fastening system. Well, then we wish to build our own test machine. This is the test machine for the brackets. So we have managed to collect the data from bolts and the T-clips, but nothing about the brackets. So we tried to build this one. This is hydraulic actuator. Shows us the force acting on the guide rail. We fixed the guide rail here. And we placed sensors, the donut sensors, and the LVDT to show the displacement or some movement on it. We managed to build this structure, but we're still working on the PLC programming, because we have to show the seismic effect, I mean the impact force effect. Now we managed to load in one cycle but there is still to work done for impact. We wish to do two different conditions. One is, as you can see, hydraulic actuator affects the guide rails in this direction, so towards the bracket. Well, then we wish to turn back and force towards the guide rail. Then we will say that our bracket has been damaged in this test. So we still work on this job. We only managed to read the sensor's data. Maybe next symposium we found the results and the present. Okay? Thank you very much.